Let's talk about mathematical logic. In mathematics, we often see statements which are sentences with two possibilities. Either they can be true or false. Let's look at some examples. First, we have the statement, "I like maths." This is obviously true. Secondly, we have the size of the set, A and B, is 2. This is also true. Next, 1 plus 1 is 3. This is of course false. Another statement is, a triangle has 4 sides. This is also false, because a triangle only has 3 sides. Let's give some types of sentences which are not statements. First, questions like, what is a number, are not statements. Commands like, eat my pie, are also not statements. We can see that it is not meaningful to talk about the truth values of these kinds of sentences. Now suppose X and Y are statements. There are mainly 4 connectives that we can use to form new statements from X and Y. The first one is we take the opposite of X. We usually say that it is not X, or the negation of X. Then, we also have X and Y, and X or Y. The hardest one is probably X arrow Y, which is the statement, if X, then Y. It is sometimes called the conditional. Let's see an example of how we can combine statements. Consider the 4 statements A, B, C, and D. Suppose we want to form the statement A and not B, arrow C or D. First, we know that the arrow means if the things on the left, then the things on the right. So let's change the color of the arrow and write down if and then. Now, let's look at the things on the left. It is A and not B. Let's change the color of and write it down. Then, we put the statement of A and B before and after. Since we need the negation of B, we want to make sure that we add the word not before remember to bring an umbrella, and because of how English works, we also need to add the word do. So not B actually means, I do not remember to bring an umbrella, or you can say, I forget to bring an umbrella. The second part of the statement is C or D. So after putting them in place, we have the whole statement which says, if it rains tomorrow and I do not remember to bring an umbrella, then I will buy an umbrella or I will get wet. Now let's do the opposite, translating a statement into symbols. Suppose we have the statement, if I cannot pass the test, then my mother will be very angry and she will not cook me dinner. First, let's identify the connectives. We have the if-then structure here, so let's change the color and write an arrow in the middle. We see a not between if and then, so let's put a not before the arrow. We see an and, so we put an and after the arrow, and then we have another not, so we see that this statement takes a structure like this. Now, we just have to define the keys for the smaller statements. The condition is, I cannot pass the test. Here, we want to make sure that the component statements that we write down are positive or affirmative. So instead of writing X as, I cannot pass the test, I write, I can pass the test, and then negate it. Next we have, my mother will be very angry. So let Y be, my mother will be very angry, and put the Y there. Lastly, we have not something, where that something is, she will cook me dinner. So let's define Z to be that, and put it in place. So the whole statement is, if not X, then Y and not Z, where X, Y, and Z are defined as written. It's time to talk about truth tables. A truth table shows all possible truth values of 2 or more statements. Let's begin with the easiest example, the negation. That is, we consider the truth values of a statement x and its negation, not x. We know that x can be either true or false, which are represented by t and f respectively. The negation of x is defined such that it is false when x is true, and it is true when x is false. So this is the truth table for the two statements. Next, we consider the connective or. Here we have two statements, x and y. Each can be true or false, so there are 4 pairs of possible truth values in total. For x or y to be true, we require that at least one of x and y are true. We see that only the last truth value is false, and the rest are true. Let's move on to complete the truth table for the connective and. With the same set of truth values of x and y, we note that x and y is true only when both x and y are true. As a result, only the first truth value of x and y is true, and the rest are false. Now, let's consider the truth table for the conditional x arrow y, which is probably the most confusing so far. The first case is straightforward. If x is true and y is true, then it makes sense that the implication x arrow y is also true. The second case also makes sense. If x is true and y is false, then of course I cannot say that y is true when it is given that x is true, because I already know that y is false. The remaining 2 cases, however, have to be interpreted carefully. In both cases, I know that x is false, and I have to determine whether x being true would mean that y is true. But the whole point is x is not true, so I have no way to say that the implication is false. Since a statement is either true or false, we must then say that the implication is true. This can be more easily understood by considering a concrete example. Suppose the conditional is, if you pass the exam, I will buy you an ice cream. Think about when I lied to you. If you passed the exam, and I did buy you an ice cream, then I fulfilled my promise. If you passed the exam, and I did not buy you an ice cream, then I had lied to you. However, if you failed the exam, then no matter I have brought you an ice cream or not, I have not broken my promise. My promise was only applicable when the condition that you passed the exam was fulfilled. So, by thinking about the truth values of statements as whether a promise was broken or not, it should make sense that the last 2 cases of the conditional are true. After understanding the concept of truth tables, we can now talk about the equivalence of statements. 2 statements, x and y, are equivalent when all their corresponding truth values are the same. And we write a double arrow between x and y. Let's begin with an easy case. Is not x equivalent to x? Let's draw the truth table. We have already seen the truth table for x and not x earlier, so we just need to add 1 extra column for not x. To fill in the truth values, we just need to switch the truth values with not x. Of course, after switching the truth values twice, they become the same as the truth values of x. So indeed, not x is equivalent to x. Let's look at more examples. Is x and y equivalent to x or not y? Again, we construct the truth tables for x and y, and x or not y, and check that their corresponding truth values are the same. We have already seen how we can arrive at the truth table for x and y. For x or not y, we first write a column for not y, and form the statement x or not y by looking at the columns for x and not y. Recall that x or not y is true when x is true or not y is true. For the first 2 rows, x is true, so x or not y is true. For the third row, both x and not y are false, so x or not y is false. For the last row, not y is true, so x or not y is true. Now, if we compare the two columns for x and y and x or not y, we see that the truth values are not the same. Therefore, x and y is not equivalent to x or not y. Next, let's consider the conditional x arrow y. We can switch the positions of x and y and form another conditional y arrow x, which is called the converse of x arrow y. Now we ask, is x arrow y equivalent to y arrow x? Let's draw the truth table to find out. Recall that x arrow y is only false when x is true and y is false. So similarly, y arrow x is only false when y is true and x is false. Now compare the two columns. They are obviously not equal, so we can conclude that x arrow y and its converse are not equivalent. Then we consider x arrow y and not x or y. We already know the truth values of x arrow y. To form not x or y, we first write down the truth values of not x and look at the two columns of not x and y. For the first row, y is true, so not x or y is true. For the second row, both y and not x are false, so not x or y is false. For the last two rows, not x is true, so not x or y is true. Now compare the two columns of x arrow y and not x or y. We see that they are exactly the same. So, we can conclude that x arrow y is equivalent to not x or y, and this result will be useful later on. Let's consider one more example. This time, we need to check the truth values of not x or y and not x and not y. For not x or y, we first write down the columns for x, y, and x or y, then swap the truth values of x or y to get not x or y. We have false, 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 true. For not x and not y, we need to write down the truth values of not x and the truth values of not y. Then, not x and not y is true when both not x and not y are true. So not x and not y is only true in the last row. Evidently, the truth values of not x or y and not x and not y are identical, so they are in fact equivalent statements. Let's wrap things up by writing down some properties of statements. You should be able to notice the similarity of some properties with the properties of sets. The first two properties are not x is equivalent to x, and x arrow y is equivalent to not x or y, and we have already proved them using truth tables. The third property is commutativity, which is the freedom in swapping statements using the connectives or and and. Similar to sets, this is the consequence of our definition of the connectives. Another consequence is the associativity, which is the freedom in order when three statements are connected together by two ors or two ands. Next, we have distributivity, which is again very similar to sets. Also very similar to sets are the De Morgan's laws, and we have already proved one of them earlier. The last property that I want to talk about is perhaps the most important of all, and it involves the conditional x arrow y. The property is that x arrow y is equivalent to not y arrow not x, which is called the contrapositive of x arrow y. While we can use truth tables to prove it, we can arrive at a result faster by using the above properties. Since we have a conditional, it is natural for us to apply property 2. Now, not x or y is equivalent to y or not x by commutativity or property 3. In order to use property 2 to convert this back to a conditional again, we'll use property 1 to write y as not y. Now we can apply property 2 to finally write this as not y arrow not x.